This is version B, Solutions for Data Analysis 2017. So, as ever, Section A questions are going to be about vehicle registrations, because vehicle registrations are on page 2 of our datasheet. So, initially looking at describing the trend in vehicle registrations from 2011 to 2015. So we're looking at this section here. You've got the even numbers not labelled, but they're the ones in between the odd numbers. So this section here, we've got a trend that is quite clearly increasing. So in our answer, we are going to need to specify what it is. So we have the trend is increasing. So for our second bit, we are asked to calculate the number of vehicles registered in 2002, and we are dealing with the vehicles. So 2002, we are told, is 2% lower than 2002, and we are told that 2015 is 876,000. So for part B, we've got 2002 and we've got 2015. So using the numbers that we've got, for 2002, if we have our old one at 100%, then by the time we get to 2015, we've got 2% lower, so that will be 98%. We know from this section how many vehicles were registered in 2015. So we have 876,000. So to find out this one, if this is 98%, then what we can do is 876,123. If we divide it by 98%, then we'll work out what 1% is. And then we can times our answer by 100 to get what 100% is. So the shortcut for doing that would be, if we were going from here to here, we would times by 98 divided by 100. So that's the same as 0.98. So if we are going backwards, if we are going back in time, we're dividing. So what you'll find is actually the equation using a percentage multiplier will get you there in one step rather than the two. So we end up with this divided by 0.98, and that will give us an answer for 2002 of 893,877.551. Now, even though your exam paper will say to write everything to 3 significant figures, on the front, it's worthwhile writing out your full calculated display once, just so that if by some accident you do something odd with the rounding, that you can still get back to your original answer. Really useful for when you go through and check your answers, which obviously everybody does at the end of an exam. So we know how many vehicles we've got in the third quarter. Okay, so part C, number of cars registered in the third quarter of 2002. So we want cars, and we're doing 2002. So we've just worked out vehicles for 2002. So need to do cars. So this is the bit where we know that car registrations are the same proportion, and this is just being used for convenience for the other part of the datasheet. So part C, we know the number of cars registered, or the number of vehicles registered in 2002, because we know that from part B. So we have 8, 9, 3, 8, 7, 8. It's good practice to use the full form rather than the rounded form where you can. And then we want the cars. So we are going to have to times by the percentage that is cars. So if all vehicles is 100%, then cars is 81.3. So we will times by 81.3%. So that is going to be the same as times by 81 and divide by 100. So we have 8, 9, 3, 8, 7, 8 times by 81.3 divided by 100. Obviously, you can also do that as a percentage multiplier if you're happy with that. So that is 7, 2, 6, 7, 2, 3, and to 3 significant figures, that will be 7, 2, 7, 0, 0, 0. So 3 significant figures, first 3 numbers, and remember to fill the rest in with the zeros. Okay, so percentage change in the number of vehicles registered in the third quarter of 2002 and 2014. This is a slightly trickier question because what we're looking at is we've got 2 things that we know. So, from this bit of information here, we know that to get from 2015 okay, so to get from 2015 back to 2002, we know that we drop 2% from here to here. So if this one was at 100, then we drop 2% down to 98%. So to go from here to here, we would times by a multiplier of 0.98. So divide by 100 times by 98. But we aren't asked for how do you get from 2002 to 2005. We are asked for how do you get from 2002 to 2014. So, if we were doing 2014 to 2015, this one would be at 100% because that's the older one. And this one, we have an increase. So we have an increase of 8%. So we'd go up from 100% to 108%. So to get from 2014 to 2015, we've got 108, so we have a multiplier of 1.08. So what we actually need is to go from 2002 to 2014. Now, we don't have a path direct from here to here. So, what instead we have to do is we have to go along the path at the top. So, if you're going forwards in time, we're going to times it. So, we start off putting 100% in at our very beginning. So, start off at 100%. Can't go directly here. So, we're going to have to go to 2015. So, we times by 0.98, which gives us the 98 we expect. So then we need to go the step back to 2014. So to take that step back, going forwards in time, we times. So going backwards in time, we will divide. So what we end up with is 90.7. So, the percentage change from 2002 to 2014, it's gone from 100% down to 90%. So, our percentage change is going to be 90. So, percentage change, it's going to go down. And we've gone down from here to here by 9.259. So we've got a percentage change of minus 9.26%. And that will tell us what the percentage change is for our third quarter. Section B is our section on snooker. So we are looking at the points in the frames of the final, written in a normal way for recording results of first person, in this case Neil Robertson, is the same first in each section, and Liang Wenbo is the second one here highlighted in little pink circles. We are told already that the mean and standard deviation in these 15 frames Now, in this particular question, we are asked only about the last 10 frames of the final. In the question, it gives us Neil's mean and standard deviation, and we're asked to compare the mean and the standard deviation found in the first section. So Neil has a higher mean, but the important bit here is in context. So this higher mean suggests he scored more points each frame. And looking at the two standard deviations, Liang has a lower standard deviation, so his points or his scores were more consistent. So section C is the predator-prey relationship. We're told about snowshoe hare pelts in thousands and Canadian lynx pelts in thousands. So the correlation coefficient, we are given the dates that they want us to look at. So what we can do is, if we enter those into the calculator, sensible first step once you've entered them is to double check that you have the number you're expecting. It sounds daft, but you should have 10 of both, so the columns should be the same length. We are then going to calculate, and we've got two variables because we have hares and we have lynxes. And so it will give us all the information about a mean, standard deviation, but actually the reason for going in here at this point is to check this n value. If your n is what you expect it to be, that gives you a really good indication that your settings are right. So if we want the correlation coefficient, we go into Reg. It's a linear relationship we're expecting. So we'll have AX plus B. So R is 0.91765568, and that's our correlation coefficient. So so 3A, we've got R equals 0.9177. So compare the correlation coefficients in context. So this in context bit is important. So our first one that we were given is 0.912. Now 0.9177 or 0.918, that's slightly bigger. It's not massively bigger, but it is a tiny bit bigger. So we know that the two time periods have got really similar but both very strong linear relationships between their two variables. So the linear relationship between hare and lynx population so this fact that we're talking about the hare and lynxes basically puts it in context. So we've got a linear relationship between hare and lynx. The closer it is to 1, the stronger it is. The closer it is to 0, the weaker it is. So we've got a really strong relationship here. So linear relationship between hare and lynx population is strong for both time periods. Now it's a tiny bit stronger, so 6 thousandths stronger in this first time period. So it's a little stronger in 1875 to 1894. Part of the reason for just clarifying that is because you may well end up where your second set of data, or one of the sets of data, is a little bit further away. So it will either be kind of 0.99 or down at 0.8 something. So at that point you'll need to tell us which one's stronger. So for part C, we are still using this same data set, which means we've actually already got it in our calculator. So calculating the equation of the regression line. This is beautifully easy because you already have, from when you worked out R, the information on your screen. So we've got, it tells you at the bottom, y equals ax plus b. So we know what A is, we know what B is, so we can just put these numbers into the equation. So we have y equals 0.382 x plus 12.2. So we then have to interpret the value of the gradient. So our gradient is this 0.382. And again, as ever, it is in context. So we need to be talking about hare and lynx. So we have a gradient that was 0.382. So in context, this tells us that as the population of hare, so population of hare is our x-axis, so it's as the population of hare increases, by, now normally we tend to have as the population increases by 1 only. Here we're looking at thousands. So as the population of the hare increases by 1,000, the population of lynx now, because this is positive, it's going to increase. So we've got two ways of writing this. We could write it as 0.382 thousand, or we could write it as 382, which is the same as 0.382 thousand. So we're looking at the context. We've said basically what's on our x-axis, one of the units, what's on our y-axis, and the fact that it increases, and we've used the value of our gradient. So, use your regression equation to predict the links. So we are going to be predicting the links when there were 10,000 hair. Now, hair measured in thousands. So here we have 10,000 hair. So we know that x is going to be 10. And we need to predict the links. So 2-mark question. This tells us we are going to have to show our substitution. So we had our equation in C part 1. And we know that the hair is x, and that's going to be 10. So into this equation, we've got y equals 0.382. Now, this is where the x would go, but we know x is 10. So stick the 10 in brackets and write it where the x would be. Now, depending on who you are, either you stick this into your calculator and work it out, or you can also put it into your graph and if you have it on your graph, it should look a little bit like this. And we want to calculate y. So we can do that with gsolve, ycal, and our x value was 10. So it then tells us that our y value is 16. So we have 16,000 links. Okay, so for part 4, use your regression line to predict. So predict hair when there were 10,000 links. Links was our y, so we've got 10 for our y. So, yeah, that's fine. Part 4, we've got the same equation, only this time we're putting the 10 where the y is. So that's the bit where we're substituting it in. And that is equal to 0.382 x plus 12.2. Now, by a very happy accident, from when I wrote the paper, we can go gsolve, and we are calculating x, so we need xcal, y equals 10. Now, we then come up with what looks like a really odd answer. In reality, this would never happen. Because what this tells us is our prediction for a year when there were 10,000 links is that there would be minus 5,000 hares, potentially zombie hares. Now, this is obviously not right. At best, you would be predicting there would be 0. So we would be looking at minus 5.71 thousand links. No, 1,000 hares. Now, obviously, this isn't a thing. And that's purely and simply because I chose a number for our y value that was too small. It does, however, make question 5 really obvious. So, comment on the reliability of your predictions. Which is more reliable? Hopefully, anybody can see that 16,000 links is going to be a more reliable option than nearly 6,000 zombie hares. Now, in reality, they're not going to give you something that's that easy. So we initially tried to predict with 10 here. So if you look down, you've got, this goes down to 9 and goes up to 137. So 10 is between 9 and 137. So that one's fine and reliable. Our links, our lowest value that we've got is 12. And then it goes up to 80. So 10 is inside this data set, but is outside the range for this data set. So the reason that the second prediction is less reliable is because 10,000 links is outside the data set and 10,000 snowshoe hares, 10's between these two values, so it's inside the data set. So even if we'd given you a slightly more sensible number so that it worked, you're looking at either inside or outside the data set. So 10,000 hares is inside the data set. So is more reliable than 10,000 links, which is outside. So realistically, the two reasons that a prediction is unreliable is if you have a correlation coefficient that is close to 0. Ours was close to 1, so that it's not true in that case. Or if you have a prediction value that's outside the data set, which is what's the case with the links here. Question 4 is on fetal growth. Our data sheet doesn't tell us much beyond the fact that it's a normal distribution, which means you can either use the normal distribution on your calculator or normal tables. So there are a certain set of things that you are always going to need to know with normal tables. We are going to need to start off by knowing what mu is. So mu is the mean, and in this information we've got the weight of a fetus is following a normal distribution with mean 146. So we have a mean at 146. And then we're going to need to know our standard deviation. And our standard deviation is 19.53. The next thing we are going to need to know is our x, and our x is our value in context. So our value in context and once we've got that information, or to be fair, if it's a slightly different question, we will also want to know the probability.
I think it's a great history. I think it's delicious. I think it's well executed. I think it's very, very clever. One of the great challenges.
So the bit with the context, you are also going to want to know whether it's more than or it's less than. So that'll do. Okay, so when we know the context, the number in context, we're also going to want to know whether it's more than or less than. So for this one, the number in context, we are doing weight less than 156. So in context, we are doing 156 and it is less than.
We now have to make a decision. So what we're going to do now is ask you to step outside.
So this will seem like a slightly strange set of things to have to do, but we need to know what our Z value is. So our Z value, that equals our X value, take away our mean, and we divide that by our standard deviation. This is the thing we need to know, and it's a thing that we have to work with quite a lot. So it's worth writing down this set of information just so that you've got it to be working with in a moment. So
Alex's food has continuously been different. I liked that scenario.
that'll do. Right, so first off, we've got Z. Now that's going to equal our value in context, and then we'll have to take off the mean, and we divide by our standard deviation.
I like Sharon's flavours. I like the fact that Sharon's tart wasn't sweet but tart. I'm surprised how big flavour it was. It was too much to all. Something quite intriguing about Sharon.
And this is a thing that can come from our calculator. So about that. So we need to know the probability that big X is less than or equal to little x.
We're definitely taking 2, right? Who else is good enough to go into knockout? That's the question.
Now, this probability is going to be equal to the probability that Z is less than or equal to our value of little z. So,
The first contestant going through to knockout route.
so if first off we work out our z value, we are expecting
The second contestant
divided by
going
19
through to
point.
knockout route.
We've got a z value that we are expecting at 0.512. So that equals 0.512.
Final contestant going through.
So this is going to be 0.5120. Now, slightly weird bits.
Very well done.
We are doing stats. It is a distribution that is normal,
I'm sorry.
and we use the middle one. So, for this, we don't know the lower bound, so we just put in something big and negative. We know what the upper bound is, it's 156. We know what our standard deviation is, it's 19.35. And we know what our mean is, it's 146. So, it tells us our probability, and it tells us what it thinks our value of z would be. And that gives us a really nice double check that we've done the right thing and we've put the right stuff in the right place, because that's the same as the value that we got for z. So we've then got our probability up at the top, and although everything in the world of use of maths is 3 significant figures, this bit isn't. Here we need 4 decimal places, so we have that equals a probability of 0.695, would be a 6, but we have to round it, and that then gives us a probability of things that have got less. Now, if we go back to the original question, we are asked for a percentage. So to turn this into a percentage, we are going to have to times by 100. So we end up with 69.57%. So a lot of this information is going to stay the same when we look at question 2. So part 2, we're still dealing with a fetus of 16 weeks. So our mean and our standard deviation are going to stay the same. Only we want a weight of more than 160. So the things that will change. Our number in context is now 160. And we want more than, not less than. So, this means that obviously our z value is going to change because our x value is going to change. And our probability at the end is going to change. But actually, all the rest of the information is going to stay the same. So, context. We want the probability that x is more than our number in context. Then we're going to want that Z is more than our number in context. So Z, we're going to need to know what X is to be able to work out what Z is. So we now have a lower bound because we want more than this, and we don't have an upper bound because we are allowed giant fat babies. And then the mean and standard deviation is the same. So we have a lower bound, so our Z value should come in at 0.7168. Our Z value should come in at 0.7168. And this is the bit we have to be careful. This value of P is smaller than 0.5. So, because this is smaller than 0.5, although we now know our probability, we need a line that we write down before we get there. So, when it is less than a half, we need to write down 1 minus the probability of Z. Then we have this sign here. We flip it the other way. No, and we keep everything else the same. And then from there, then we can write down our probability. And that is 0.2367. And if we need it as a percentage, as in this question, that's going to be 23.67%.
If they can hold their nerve, they're going to be absolutely fine. But I tell you what, this is a nerve-wracking round. Without good choosing, there's no
Okay.
and there's no great chewing.
So we still need the mean, standard deviation, thing in context. We were finding out the probability. So you will always have 3 out of the 4 of these values if you look for them.
It's really important because at the end of it,
So,
3 of you
part 3.
1 hour, 20 minutes.
Our fetus is considered to be small if its weight is in the smallest 10%. So, the smallest 10%, we've got a normal distribution that looks a bit like this. The smallest 10% would be this little section down here.
I can put fish, I can do meat, I can do veg.
So, we don't know the context this time, but we do know the probability, smallest 10%. So 10% is 0.1. Writing it as 0.10 isn't technically correct, but they can't kill you for. So, we don't know our number in context, so we are going to have to take out all of our numbers in context because we don't know those.
Without a recipe. Its own factories without a recipe. Presentation to Richard is going to be quite difficult.
Okay,
How's he going to make it look wonderful?
so the thing we do know is that we've got a probability of 0.1. So, because we don't know the context, it is still a distribution, it is still normal, but this time we need the inverse. So, looking at this, the tail is to the left. The area, that's our probability, so the amount we coloured in. So that area there, 0.1. So area is 0.1. And we've already got our mean and our standard deviation in there because it remembers it from whatever you set last time. So when we press equals, we get our value of x straight off. So we have equals 0.10. So we know that this is 120. Actually, 121's more sensible. Which means we now know our number in context. Which means that we can then put it in here and work out a value of z. So we've got 121, take away 146, divided by 19, delete 0.35. And that gives us an answer of minus 1.28. So that's going to be minus 1.28. And that's part C sorted. So effectively, we've got a value here that is 121. So, last off, a fetus is considered to be large if its weight is in the top 10%. A fetus of a 36-week generation. Right, so, because we've been given the information that we are no longer dealing with a 16-week, we don't have the same mean, we've lost the standard deviation, we don't know the context, or any of that. And that's pretty much all we know at this point. So, a fetus is considered to be large if its weight is in the top 10%. So the top 10% is going to either be more than, and then dealing with 10%, or if it's in the top 10%, it's greater than or it's more than 0.9. So we're looking at something that is more than 90%. We know it has a mean of 28.13. And we don't know the standard deviation. But we do know that our value in context, help if I write it in the right place. We do know our value in context is 3291. So our probability, it was in the top 10%. Okay, so we can work out our standard deviation, because if you look at this, if we knew what x was, if we knew what z was, we can work out our standard deviation. So if we employ what feels a little bit like a cheat, and kind of is, what we can do is we can say if the mean was nothing and the standard deviation was 1 and the probability is what we want, then we can still work out our z value. Then this will give us a value in context of what is effectively z. Because if you make your means 0 and your standard deviation 1, then you get z as your standardized variable. So what we are then trying to work out is what z is. So we have a distribution that is normal.
What are you making right now?
Well, so I'm going to do...
Now we don't have either of our upper or lower bounds, which means we have to go and an inverse. So if we want to know the probability that it is more than 90, then our tail, because we go that way, and we want to know more than 90, our tail is going this way, which is right.
Thank you, Will.
Our area
Couldn't find any breadcrumbs, so I'm doing...
is... Actually, let's make this look like it should do. So if we want this section, if we go with this bit, so we want it more than this, so not in this. If we go for our tail that way, and then we've got an area of 0.9, because that's the bit we coloured in. Now, these values that are here are currently for our 16-week fetus. So if we use these values to standardise, we end up with 1 here, 0 here, and then it gives us a value that is z. So we can work out that z equals 1.28. So if we know what z is, we can go 1.28 equals our number in context
Lorenzino, up your cut, my friend.
minus our mean and divided it by our standard deviation. This is the thing we don't know. So to work out this, we're going to have to rearrange. So menu 1. So we have 3291 minus, no, that does not say what, 1 minus 2813, and then if we rearrange this, we can times by the sigma, divide by the 1.28. So if we times both sides by sigma, then we'd end up with sigma times this, but we want sigma on its own. So if we divide both sides by 1.28, then what we get effectively is this. These two cancel, so we're just left with sigma on this side. So we've got this, we divide it by 1.28, and we get an answer of sigma, where are we? Sigma equals 373. So that's what we're asking for.